Let's delve into gravitational potential energy. You know that potential energy is the energy saved in a system. Gravitational potential energy is the energy saved in a system due to gravity. So let's say gravitational potential energy is the energy an object has because of its position in gravitational field. Here I have a ball acted by a downward force of mg. I'm gonna take it to a higher altitude, let's say for delta H. And so I need a minimum force of F equals mg to overcome the weight and make that displacement. The work done against gravity is the force times displacement. Force is mg here, and delta x is delta h here. This W also is called gravitational potential energy. So let's say gaining gravitational potential energy, changing gravitational potential energy, is the weight of the object times the change in altitude. For simplicity, we usually take the ground state at the minimum altitude the object is in. And then the new altitude is going to be taken instead of delta H to be H. So we can say potential energy is mgh, provided we have already supposed that the minimum altitude has zero gravitational potential energy. It's up to you, but it's very simple to take it as zero. Notice that potential energy is a property of a system, not of an individual particle. Here I have a helicopter at a specific height. Let's say the height is h. It's very usual to say energy saved in a system and we write EP equals mgh. But it's not saved in helicopter. It's basically saved in a system, Earth plus helicopter. Without the Earth, there is no gravity, so there is no gravitational potential energy. Basically, it's a systemic property. But by mistake, we usually say the energy saved in helicopter. Keep in mind, there is a system. An object of mass 1.5 kilograms slides down a 4-meter long ramp that makes an angle of 30 degrees with the horizontal. So the object goes down for 4 meters along the ramp. Okay, here we are going to find the work done by on the object by the gravitational force. Gravitational force means mg, downward. Previously, I mentioned the work is defined as the effective force times displacement or force times effective displacement. Effective force is the component of the force in direction of displacement, and effective displacement is the component of displacement along the force. It's up to you to take one of these two alternatives. I take the second one. Here I have a force downward, so effective displacement is gonna be the component of the real displacement along the force. The force is vertical, so I have to make a decomposition on this vector, the vertical decomposition, to make the effective displacement. Let's say the effective downward displacement is delta H. Okay, in this right triangle, I have a vertical side for delta H, and here this is the opposite side to 30 degrees. I use sine function. Sine of 30 degrees is opposite divided by the hypotenuse. Sine of 30 is a half, so delta H is a half times 4. It's 2 meters. So the object really goes down for 2 meters. This is the effective displacement. We won't use 4. So let's find the work done. mg, the force, times effective displacement. Now it's 2 meters. Let's plug in the values. G is given for 10. It's very easy. Mass and displacement. 30 joules. The last part of the question, what's the change in gravitational potential energy? Delta EP. Let's say delta EP is the final EP minus initial EP. Okay, EP1. Here, I mentioned it's very usual to take the ground state, the minimum height the object can have, to be zero gravitational potential energy. So let's say EP here is 0. So EP2 is 0. EP1 is mgh, and the mgh has a value of 30 joules. So delta EP is going to be 0 minus mgh, negative 30 joules. The reason when the object goes down, basically it's releasing potential energy. When you take it up, you are fighting against gravity, you are saving potential energy in the system. But when you release that, it's releasing potential energy. So change must be negative. The last point I should mention is the path. You see that the object goes down for 4 meters. I can show you something. Let's say the object is here and it will have a vertical displacement of 2 meters. But here the object can go on the ramp for 4 meters, or maybe it may have a steeper ramp for 3 meters, but same vertical displacement, or this ramp, or even this very crazy path. All of them will have the same vertical displacement. So keep in mind that always we say the work done by the gravity is mg times delta h. The net vertical displacement is totally independent of the path. So if I have something like this, the object is here. If I have a very, very strange path, but I know the vertical displacement to be 2 meters, I will have the same answer. So don't bother yourself to check the path and find the change in gravitational potential energy point by point. It's not necessary. Just delta H, the vertical displacement, is enough. Thank you for watching this video. See you soon.